Good evening, Statistical Methods class. This is Mr. Marquetta, and I'm here to help you today with Chapter 2. We're going to talk about all of the different examples and techniques that you'll see in Chapter 2, have to do with data. We're going to use Zoom today to describe these ideas because the weather's a little bit crazy, and I live in South Jersey. It's a little hard for me to travel right now, so I sent out an email yesterday inviting everyone to come today, and if you couldn't come, please watch this video. This video shouldn't take more than an hour of your time to sit through and just learn the ideas with us. We do have a couple of students in attendance. I appreciate those of you who could make it. And what we'll do now is we'll start talking about Chapter 2. Today specifically, we're going to cover just sections 2.1 through 2.4. And as you can see, the topics are stem and leaf graphs, which are also called stem plots, line graphs, and bar graphs. Doing those will feel like the 5th or 6th grade. You probably studied that material already. Then in Chapter 2.2, you'll see histograms, frequency, polygons, and time series graphs. I would just call those kind of like advanced 5th grade statistics. They're the same ideas, they're graphs, but they're a little more detailed and not that hard to understand. After we have a little conversation about them, you'll understand them really well. Then 2.3 is measures of the location of data. It's an interesting lesson that most students at this point have never seen before. It's about percentiles and also quartiles. A lot of people have already learned about quartiles, but percentiles come into play in Chapter 2.3. And then Chapter 2.4 is box plots, which is a really great enrichment and application of quartiles. So we have 4 really great sections here that we're going to work through. And this was originally one whole PowerPoint, and I cut it in half to be 2 sections. So Chapter 2 is in 2 parts, feeling like that would make it a little bit more time for the students to have time in class to practice. This should be over with within an hour. The class is 2 hours long, and I'll be here with you to study with you and answer questions in your assignment if you should need any help with that. And we can do it that way because we're a 13-week course, so we have a little bit of a different kind of schedule. So anyway, we're going to go today through these 4 sections. Here are the objectives. By the end of this chapter, students should be able to display data graphically and interpret graphs, recognize, describe, and calculate the measures of location of data, recognize, describe, and calculate the measures of center of data, and recognize, describe, and calculate the measures of spread of data. Those second 2 objectives are actually reserved for next lesson. This lesson is chapters 2.1 through 2.4, so it's really the first 2 objectives, but it goes in connection with the rest of Chapter 2, which we're going to have a lecture on Wednesday about. Okay, so let's talk now about Chapter 2.1, where we're trying to think about stem and leaf graphs, which are also called stem plots. And we're also going to talk about line graphs and bar graphs. So first, let's talk about stem and leaf graphs. To create a plot, divide each observation of data into a stem and leaf. The leaf consists of a final significant digit. So for example, 23 has a stem of 2 and a leaf of 3. And then the number 432 has a stem of 43 and a leaf of 2. Okay, it's hard to read math. When you're trying to read that, it might be hard to digest and understand what they're saying. But what they mean is take every number you can see and kind of chop off the ones place. I'm going to do some writing to make it kind of clear when we do the exercise on the picture, rather on the slide, so that you can see what I'm talking about. Scrolling in a little bit. If you look at these numbers, because these are the numbers we're going to use in our example. When we're trying to figure out stems and leaves, we're actually going to use for the first number, this digit is going to be the leaf. For the second number, this digit is the leaf. In other words, you always take that last digit and those are your leaves. The stems are the things that you see repeating. So here we have a 3, right, as a stem. And then here we have, I'll use another color. How about green? Okay, 4. Notice I have 4 is going to be a repeating stem. There's another 4. And then when I get to the 5 will be another one. So in other words, the point is, my friends, the stems are the tens digits and the leaves are the ones digits. If you have larger numbers than that, then what's most important is that the leaves are actually the ones digits and that the first part is the stem, whether it be in that case that they showed up there, 432. In that case, we had a leaf of 2, but then the stem has to be something a little bit larger than usual, 43. So in the case that it's a larger number, the stem is the first 2 digits, or it could be the first 3 digits and stuff like that. So anyway, you have stems and leaves, and what you do is you split every number into its stem and its leaf, right? Then after you're done with that, you create this interesting looking chart. It looks a little bit like this. You have a line. Let me get a little bit closer so that you can see it now. Okay. So we'll draw a line like this. Okay. And then you'll notice that we have, and I'll try to color code it so that it makes sense. You'll notice that we do have one number that is in the 30s. It's that one. So I'll put that one here and I'll make it red like that. Now try to imagine that I have like something that I can draw on easy. Okay, I'm trying to do the best I can drawing with the tool on here, so it might look a little funny, but that's how you express 33 in stem and leaf. Now we have 3 numbers that start with a 4. I'm going to use blue to show those numbers. Here they are. And you'll notice that the stem is 4 there. However, the leaves are 2 and then 9 and 9. So it should be like this. It looks a little funny. I made it blue so that it matches the box. But the point I'm trying to make is you should be able to read a stem and leaf chart like that and say, okay, the first number is 33, the next number is 42, then there's 49, then comes 49. Like notice that between 299 there are no commas. It kind of looks like the number 299. It's not. They are leaves. They're supposed to be 42 and then 49 and then 49. Carrying on with the 5, this time we'll use purple. I'll use a rectangle to show you the 5s. These are the ones that have a stem of 5. So they have a stem of 5. And they have leaves of 3 and then 5 and 5. Notice in both the stem of 4 and 5, you see some repetition there. That doesn't happen every single time, just for this particular data. That's what's happening. It happens to be 5, 5. You'll notice when we do 6, it looks like it kind of ends a little bit that way too, but that just happens to be the way this data is. That's not something that you can always rely on in any way. Let's do the next one here in green, using a rectangle to show. The 6s, here they are. Well, there's a lot of them. So we'll use green ink to put in the 6 as a stem, and then put in all those leaves, which will be 1, 3, 7, 8, 8, 9, 9. Okay, and my numbers ran off of the page a little bit, but I know that you can see them. I know you're understanding the idea. Carrying on, we'll do the 7s now. Let's pick another color. I'll pick light blue this time. All right, so we'll do the 7s. Here they are. All right, and then we'll draw those in. So it'll be a 7 as a stem, and then the leaves are 2, 3, 4, and 8. And then we have 8s. For 8, I'll use black. Okay, and then we'll draw into the stem 8. And the leaves will be 0, 3, 8, 8, 8. Okay, so as a reminder, when you see a repeating leaf, you have to write it, repeat it, 8, 8, 8. You have to keep writing it until you have as many as you're supposed to get. One last thing, this one I'll do in dark red. is the 90s, is these figures here. And those 90s have a stem of 9, and then they've got leaves of 02, 4, 4, 4, 4. Okay, so we're going to ask you to give us this whole thing right here as your stem and leaf plot. It has all the stems on the left with the line, and then on the right it has all those numbers, and they are leaves. Something that's interesting about a stem and leaf plot is you kind of turn your head sideways and look at it. You can imagine it as a distribution if you kind of follow it like this. You see what I'm doing with this line here? You know, when we start studying the bell curve and different kinds of distributions and like what it means to be robust, like you can see hills and things in the stem and leaf plot if you look at it sideways, the same way you can look at graphs like this. All right, so kind of keep that in mind, and that's, you think about how things kind of gravitate towards the center a little bit. You know, that's the idea here in statistics. All right, so we'll carry on now. I'm going to get rid of all that. All right. Next, we have what we like to call line graphs. In a survey, 40 mothers were asked how many times per week a teenager must be reminded to do his or her chores, and the results are shown in this table. So here we have the number of times the teenager is reminded, and we have numbers 0 through 5, and we have the frequency of how many of them actually did their chores, right? So we have some nice data here. They act as points on a grid. It's kind of like the XY plane a little bit. What they do is they design the X and Y axes to be appropriate for whatever the measurements are. We have labels that are really descriptive. It says on the bottom, number of times teenagers reminded. It says frequency up there. And then what we do is we plot them and we kind of connect the dots using a ruler or a straight line tool. And you can see there, this is an example of a line graph. Line graphs are pretty easy to read if you asked a question about it. They're also kind of easy to draw if you're given a graph background, and you'll have cases like that when you do your assignment. So this is the line graph. And then we have bar graphs. The bar graph, and just like the line graph and the stem and leaf, you probably did something with bar graphs when you were in math class in 6th grade or 7th grade. It's part of middle school instruction. And we review it again here in statistics before we talk about the histogram and the frequency polygon, because they're very closely related, except this is kind of like the sugar-coated version of the histogram. The histogram is a lot more involved and has important parts to it that you have to understand. But if you have a good grasp on the bar graph, when you do the histogram, it all follows back and makes sense knowing how a bar graph works. So let's look at example 2.5 and think about that for a minute. By the end of 2011, Facebook had over 146 million users in the United States. Table 2.8 shows 3 age groups, the number of users in each group, and the proportion as a percent of users in each group. Construct a bar graph using this data. Something I want to just throw in here while we're having our conversation. When you see a proportion, or the word proportion, it means part or piece of something in the same way a percent does. So you'll see a lot of it being interchanged in the writing of the book that they talk, or in the ideas of statistics, that proportions and percents are kind of the same thing. In math mechanics, they are kind of different, but in statistics, they kind of mean the same thing. They mean the piece of it that has the quality. So here we have proportions, again, or pieces of it that have specific qualities. The piece of the group of Facebook users that's from this age, 45%. That's from that second age group, 36% and 19%. If you look at the bar graph, again, we have an appropriate scale drawn, and it's similar to the XY plane in that you have a measurement going up and a measurement going to the right. The measurement going to the right is a little bit more concrete, though. It's specific groups of people described there, 13 to 25 and so on. But likewise, the proportion is a pretty clear, explicit list of numbers there, and you know that you can show a bar by getting just to that level and so on. And the bars do make sense. They do follow the data. You'll see there's also important labeling there. It says ages and it says proportion and percent. So you have a nice bar graph there. We could ask questions about it. We could change the data and ask you to construct a new bar graph, things like that. So this is a bar graph. The thing about the bar graph that connects it to a histogram is usually a bar graph is not about a range like 13 to 25. A bar graph is usually about your favorite ice cream. like chocolate, strawberry, or ice, or vanilla, or it's about your hair color, or it's about your political affiliation, and it's just simple categories. These are categories too, but there's special kinds of interval or arithmetic numeric categories. And that's just what a histogram is. It's basically, instead of having different political affiliations that you could gather data about, you gather numbers and then break numbers into groups like 13 to 25 and such. And then you have the idea of the histogram where you have like something more of a scale along the x-axis that includes all the different ages that could have happened amongst your observations. And we're going to get to that in just a second. In fact, we're going to get to that right now. Here we are. So histograms, frequency polygons, and time series graphs. They're basically everything we just talked about, but like with a little more of an academic college touch to it, okay? So here's what a histogram is. A histogram consists of contiguous adjoining boxes. So let's just look back for 1 second. That last one where we were just looking at this a second ago, right? It was those bar graphs. Look, those bars are not touching. They're solid skyscrapers of their own. They're not touching each other, right? In a histogram, sneak peek, I guess there aren't any pictures of any histograms in this. There should be. That's funny. There isn't a single picture of one. Anyway, it's the same idea, but they are touching, and I'll show you one in Excel before we end our lesson today. But a histogram is a bar graph. It's just that they are touching. It has both a horizontal axis and a vertical axis, and the horizontal axis is labeled with the data that it represents, just like the bar graph, and the vertical axis is labeled with frequency or relative frequency. The graph will have the same shape with either label, and the histogram, like the stem plot, can give you the shape of the data. Remember when I drew that line? The center spread of your data. So to construct a histogram, first decide how many bars or intervals, also called classes, you could use to represent the data. Okay, so I think you'll see that as we go through here, there aren't any examples in this slide about histograms. So what I'd like to do now is show you something in Excel so that you can see what a histogram looks like. Give me 1 second to go and pull that up. Okay, so we're looking at Excel now, all right? And in Excel, you can make all kinds of great images and graphs and stuff, but I'm just going to come up with some basic data here, and we'll do something kind of like this when we have our lab. I'm just going to come up with some numbers here really quick. This is just to show you what a histogram looks like. You don't have to take notes on this or anything like that, but I can create a histogram just like this. Yeah, change the bin. Guys, I'm going off on a tangent, but what I'm trying to show you is, don't look at that. What I'm trying to show you is this is what a histogram looks like. This is kind of a poor one because there's only 2 bars. There are ways to make it that there are more than 2 bars, and then off the top of my head, I can't think about it. But notice that the bars are touching. That's what I wanted to show you. If you look, that there's not, it's like there's no room in between them where before there were skyscrapers and there were bars touching them. And the reason why is because you'll notice that on the bottom, it goes up to a certain specific place, and then it kind of carries on from that place in a continuous way. Your book isn't really giving you a lot of details about it, but when we do our lab and our activities, you'll see more details about how histograms work. We'll look at some of the textbook as well. But a histogram, as you can see, is very much like the bar graph. It's just that it shows intervals of numbers over a continuum, and that's why the bars are touching. So that's an important aspect of it that you have to note. And they describe it in a very strange way here. I don't mean to particularly mock them, but this expression here, this contiguous adjoining boxes is a bit misleading, hard to see, but it's adjoining, meaning that they're touching, the rectangles touch because it goes on continuously on the x-axis. I hope that was a good enough explanation. I'm trying to make it as clear as I can for you. That's what a histogram is, and usually it's got many more than two bars in it. The one that I was just showing you only has two because that's the default one in Excel. So let's talk now about a frequency polygon. You look at this frequency polygon and you'll think, wow, where did those numbers come from? If you look closely at these numbers, and I want you to kind of examine them with me, and we'll figure out together what they are, and you'll see after we're talking about them why they make them the way they do. I'm going to use a little, if you look at the lower bound, I'm looking at this row right here first for a minute. That one is describing specifically the point that is at 55 or so, which is right here. Okay. Now, if you think about lower bound and upper bound, now think about them as boundaries. You know what a boundary is. It is like you cannot be lower than this, it cannot be greater than that. Okay. If the boundaries are 49.5 and 59.5, it looks like all of the numbers 50 through 60 will work in there, right? And if you think about right in between those two numbers, that's where you are at this figure, 54.5. Now, looking at this frequency polygon, all those decimals, they may feel a little bit confusing, like why are those numbers the way that they are? Where did they come from? But for every frequency polygon, there is a histogram, and you can always connect the histogram with the frequency polygon, and it helps you to kind of see a little bit about where those numbers come from. When we do the activity and when we do the lab in class, we'll have a lot more experience on how to do lower bound and upper bound and what they actually mean. The way you want to look at it right now is there are 5 like this, it should be. There you go. So there are 5 that were in between 50 and 60. Put it like that. So there were 5, and that's why we're up to 5 right here. The other thing that's important is look at the cumulative frequency. It's 5. The reason why it's 5 is because this is the first entry and they're equal, the frequency and cumulative frequency. But if you look at how the next one is 10, right? 10 plus 5 makes 15. And then if you look at how the next one is 30, 30 and 15 makes 45, and so on and so forth. In this case, we must have tested 100 people. Or in this case, we're talking about percents, it's one or the other. It does say frequency here and not percent, so I'm tempted to believe it's actually 100 people. I think it's important to mention, looking at this, that the frequency is the actual number of people that got a grade on their final test score that was between the numbers of lower bound and upper bound for that category. And you could say things like, well, there were 30 scores that were in between 69.5 and 79.5. And the reason why those numbers were chosen that way was to try to reflect the idea of just exactly 10 numbers. That first one, 49.5 to 59.5, means 50 to 59. And if you had grades that were all whole numbers, but if they were, decimals for some reason, sometimes grades are, you can include that as part of your analysis there. So the frequency polygon, the cumulative frequency is not used when you're coming up with the graph. The numbers of the graph actually come from the frequencies where I drew the diamonds. Then after you draw them, you connect them with dots, and then you have a frequency polygon. Okay. In this case, what you're looking at is 2 different frequency polygons being graphed on the same graph. And it's color coded. It doesn't say anywhere it doesn't quite, but I could tell you that the first one that we saw, let's go back and look at it just one more time. The first one we saw, if you look, is the dark blue line. Look at the graph now. The light blue line has been added on. So the top set of data is the one that we were looking at before. And the bottom set of data is the new set of data that's being graphed using the light blue line. This is an example of doing more than one frequency polygon at the same time. You can make statements like up until 64.5, the second data has greater values than the first set of data, and things like that, in different wordings based on the story. In this case, based on calculus final test scores or whatever you're doing there. And then we have something called a time series graph. Time series graph is whenever you have a situation that you're studying over time, where you study something. It could be in very long intervals of time or very short intervals of time. Here you have an example of doing it in over the interval of years, annually. We're going through measurements of the annual consumer price index annually from 2003 to 2012. That's a 9-year stretch. And throughout there, every year we have a value and we plot the value, and then we see if we can make any kind of trend or prediction. This one is basically an upward trend. There's a little bit of a steepness in the middle there around 2008, and then a little bit of a leveling off in 2009. You could say things like that. Other examples of time series graphs are when you change the x-axis to have decades. You could do 1910, 1920, 1930, or if you were doing it in accounting, you might see it done in quarters. Like quarter one is January through March, and then you have April through June, and they have things that operate in quarters. You might see quarters down there. In microbiology, you might see things with minutes down there. If you're doing something in the petri dish with a population boom or something like that, you might want to measure things every 2 minutes or something like that. So these time series graphs, they kind of apply to all different sciences. One of the easiest ways to think of a time series graph, though, is annually. So here we have a great example of an annual time series graph. And just like any of the other graphs, if you're able to interpret a graph in general, this is one of the staples of that. You would always have this as one of the go-to questions when you see a time series graph here. That's what they call it. Why? Because time is on the bottom, whether it's in minutes or decades or years or days or quarters or whatever. All right, let's talk about measures of location. Now, we have measures of spread, and we have measures of center, and we have measures of location. Measures of center are the ones that we learn mean, median, and mode, because they're about how all the numbers come to the middle. Measures of spread, like the standard deviation and the range, are about how far apart and spread apart the numbers are in a list. This is about the measure of location, which is about where are certain numbers in the list. Are they first? Are they last? Are they in the middle? Are they in the first third of it? Are they the 29th out of 100? What location are they in? So the first important idea that we want to talk about location is median. And then after median, you have the idea of quartiles and percentiles. And if you understand the median really well, then you should have no problem understanding the quartiles. And then last, you should have no problem understanding the percentiles. Basically, the median is not just the number in the middle. You have to think of the median as a measurement of a set of data, such that you can cut the numbers into 2 parts that are equal parts. So it's not exactly that it's the number in the middle. It's the number that cuts the data into 2 parts. That's why when you have quartiles, you're cutting the data into 4 parts. And when you have percentiles, you're cutting the data into 100 parts. But it's hard to understand parts because 100 parts is a lot. So imagine you had 1,000 numbers and you had to cut that into 100 parts. Each part would have 10 numbers inside it. And that's what I mean by part, like pieces. So in the median, when you cut it into 2 parts, it makes sense. Each part is like 25 numbers each if it's a 50-number set. But if you have like quartiles and you have 100 numbers and you cut it into quartiles, each of those quartiles is a marker in the list of where the first 25% of the data is, then the next 25, then the next, and then the last. And that's the idea of a quartile, is it's a place that cuts it into 4 parts. And the percentiles are the numbers that cut them into 100 parts. So if you can kind of think of them in that way, then it is a pretty straightforward idea. I recommend first you really try to think of the median that way, and then when we go into the next couple of ideas, it does kind of become clear. Okay, so the median is a number that measures the center of the data. You can think of the median as the middle number, but it does not actually have to be one of the observed values. Half the values are the same number or smaller than the median, and half of the numbers are the same number or larger. So I just want to highlight, it says it is not a number. It does not actually have to be one of the numbers. And it's really important that we note it is a number that separates them into halves. So remember, that's what a median is. It's the number that cuts it in half. Sometimes the median is right in the numbers with it. Then it's all the numbers above it and all the numbers below it. But otherwise, you just think of the number that's in between there perfectly, and that's the one that cuts it in half. Okay. So for example, consider the following data. Right now, friends, I'm looking at this piece and then put them in order. You can't observe location until you have sorted the data. In Excel and on Google Sheets, there's a real easy way to highlight data and sort it. And I'll show you how to do that today too. Then order them from smallest to greatest. There you go. Now they're in order. In this case, the author is using semicolons to separate the data, which is very helpful considering that there are decimal points throughout the data. It makes it a little bit more clear. So what? There's semicolons to show. I've never seen that before. That's the first for me, but creative. Okay, since there are 14 observations, the median will be somewhere between the seventh value and eighth value. That means between 6.8 and 7.2. Let me highlight those separately, right? Take the average of them, but boom, there you go, 7. That's the answer. All right, so I hope that makes sense. That's how you find the median. If you instead had one more number at the end of there, let's get creative and put one more number here. Say that we had semicolon, okay, 13.5, right? Let's just say, for example, that there was one more number. Then what would happen is we would use this right here as our median, because then what would happen is that's the number that represents that there are 7 numbers beneath it? Yes, and 7 numbers after it. Yes, that's right. Okay, so medians happen sometimes in the data, sometimes they don't. It's the same situation with quartiles and with percentiles. Sometimes they are in the data, sometimes they aren't for different reasons. Okay, so let's clear that. Now we'll talk about quartiles. Quartiles are numbers that separate the data into quarters. Quartiles may or may not be part of the data. To find the quartiles, first find the median or second quartile. In other words, the median is Q2. Let me put a little note of that because that's really very basic and people forget that, but Q2 is the median. Just kind of want to keep that up there floating so that we remember. Okay. So first you find the median or Q2, then you find the first Q quartile, Q1, by finding the median of the lower half of the data. Now you just cut the data in half. When you did Q2 to find the median, when you found the median and found Q2, you cut the data in half. To take the lower half, what's the median of just those numbers? That's Q1. What's the median of those numbers above? That's Q3. So like it says here, and then the third quartile, Q3, is the middle value or the median of the upper half of the data. Then last but not least, after you found Q1 and Q3, if you subtract them, you get what's called the interquartile range. Now, don't let that drive you crazy. It's really very basic. It's just that when they describe it, it becomes hard to understand the idea. But the interquartile range is simply the third quartile, or Q3, minus Q1. In some textbooks, they will call it the upper quartile and the lower quartile. So you might see that somewhere and know that Q1 is the lower quartile, Q3 is the upper quartile, and so on. But if you want the interquartile range, or IQR, then all you have to do is subtract those two quartiles. Now, why do you ever need to know the interquartile range? Because when it's time to determine whether or not a number truly is an outlier, you can use the IQR to confirm whether or not it is an outlier. Let's remember for a minute, friends, what is an outlier? An outlier is a number that doesn't make sense. Listen to my numbers here, okay? 1, 2, 5, 8, 777. 777 is very, very big compared to the other numbers. It probably doesn't fit. It might have been a typo, right? Or it might just be a really extreme score in the data, which is kind of rare, but once in a while happens in statistics. An outlier is a number like that really is very far from the spread of the data. How can you tell if something is an outlier? Well, first you have to find the interquartile range, and then there's another procedure after that you have to do. But the point anyway is one of the primary applications of the interquartile range is figuring out if something is an outlier or not. So we need to know how to find the interquartile range. And the way you find it is you find the upper quartile, or Q3, you find the lower quartile, or Q1, you subtract them, and then there's your interquartile range. Okay, so let's read the description of interquartile range for a minute, and then we'll talk about outliers and how they play a role in the story. The interquartile range is a number that indicates the spread of the middle half, or the 50% of the data. It is the difference between the third and first quartile. So when they say middle 50%, They're talking about imagine data cut into 4 different parts. The 2 middle parts, which is the middle half, that's what the interquartile range is talking about, that spread. So now let's read what it says underneath in the bullet. The IQR can help to determine potential outliers. A value is suspected to be a potential outlier if it is less than 1.5 times the IQR below the first quartile or more than 1.5 IQR above the third quartile. So what happens is you have to figure out what those boundaries are. If you have Q1 and Q3, what you could do is take the upper quartile Q3 and add that figure onto it, 1.5 times the IQR. You get another number that's very, very high. If the number in your data is higher than that, then it's an outlier. Likewise, in the negative direction going backwards, you could do the same thing. You could take Q1 and subtract 1.5 times the interquartile range from it and get a very low number. In fact, sometimes it's even a negative number. When you have that number that's so low, if you have a piece of data in there that is lower than that number, that's probably an outlier. And that's the process you go through to get an outlier. Now, we'll do examples of where you test numbers to see if they're outliers and find out whether or not they're outliers. We'll talk about how you can use the interquartile range that way to figure out the fences associated with the upper and lower boundaries of where the outliers can begin. They call that a fence, by the way. The fence is that number, that whatever the upper quartile plus 1.5 IQR, that high number, that if it's above that number, it's a outlier. That is called a fence, kind of like how you fence in your yard. Some textbooks call it a fence, some textbooks don't. Now, here's the outlier. Potential outlier is a data point that is significantly different from other data points. These special data points may be errors of some kind of an abnormality, or they may be a key to understanding data. So for example, 2.13, they're saying, for the following 13 real estate prices, calculate the IQR and determine if any prices are potential outliers. Prices are in dollars. Okay, so here's what we'll do. We're going to take this data and put it into Excel now, and then we'll start sorting it and thinking about the quartiles and what the interquartile range is and what the fences are. And then I'll show you how to determine where outliers are. All right, I'm gonna zoom in a little bit so we can all see the data. All right, and I'm gonna put these numbers in now. It'll take me just a minute to write them in. 389,950, 230,500, 158. Follow along if you like with Excel. We're starting. $5 million, 387. All right. All right, so I have the data here, okay? And now what I'd like to do is sort the data. So first I'm gonna highlight all of them. I'm gonna just go like this. Sort smallest to largest, there we go. All right, now Excel has this beautiful feature in it that it does list 1 through 13, telling me there is an odd amount of numbers here. I can assume this right here must be the median because it's right in the middle. There are exactly 6 numbers beneath it and 6 numbers above it. So this is Q1, I'm sorry, this is Q2. And now if that's Q2, then that means that I should exclude this. Let me just highlight it. And now I should look at just these and think, what's the median of those? The median of those is going to be the average of these two. Let me just kind of highlight those. Same thing's going to happen here. Let's make it a different highlight. That's good. Same thing's going to happen here. So here I have Q1 will be the average of these. And then Q2 is going to be the average of these. I'm sorry, Q3 that is. So I just found all of the quartiles. I have Q1 is the average of those, Q3 is the average of those, and I found them because Q2 is the yellow one there. So the interquartile range now is, remember, Q1, Q3 minus Q1. There's your interquartile range, okay? Now, let's find out 1.5 times the interquartile range, because that's a step in your fences to figure out which outliers are there. That would be 1.5 times this number. All right, so I have that figure. Now what I have to do is find the fences. The lower fence is going to be Q1 minus 510. Well, yeah, 510 now. 510,375. All right, and now the upper fence will be Q2 plus that figure 510,375. All right, so take a look at what I found here, and I'm going to highlight these because these are my fences now. I'll highlight them in red and orange. These are my fences. What does that mean? That means these are the very boundaries of data I expect here. If anything is outside of these boundaries, they must be outliers. They are the boundaries. They're called fences. Now, how did I find them? Well, first I found the quartiles. How did I find the quartiles? I find the median. The median is the 488,800. Then I look at the bottom numbers and the top numbers, and I take the medians of those two subgroups. As you can see, they were even amounts of numbers. So I had to find averages for the two middle numbers for each of those. I used green to show that. So now we have all three quartiles. To find the interquartile range, we subtract Q3 minus Q1, and I did the arithmetic. There it is. To find 1.5 times that, we have the figure 510375. That number, if I subtract that from the lower quartile, is the lower fence. If I add it to the upper quartile, it's the upper fence. This should say upper quartile 3 here. That's not right. There we go. All right. So those are the fences. Now, are there any numbers that are lower than negative 201? The answer is no. Are there any numbers that are larger than the number 1,159,000? The answer is yes. Take a look at this one right here. I'm going to bold it and make a big deal out of it. That number is an outlier. Why is that number an outlier? Because it's outside the fence. The fence goes up to 1,159,000. And that number is outside of it. All right. So that's what we mean by an outlier and how you can determine for sure whether or not something is an outlier. We'll do more of this in class when we get together. We'll do it as a part of our lab and our assignments. Then we have interpreting percentiles, quartiles, and medians. So a percentile now will indicate the relative standing of data value when data are sorted into numerical order from smallest to largest. percentages of data values are less than or equal to the percentile. So for example, the 15th percentile of data values are less than or equal to the 15th percentile. It's all of the numbers beneath it. Higher percentiles mean many data values and lower percentiles mean not that many. So there's two things that we could say. We could say, can you find the 10th percentile of this data? Or we could say, can you tell me what percentile the number 29 would be in this data? So in other words, we either give you the actual location or they give you the actual data. The location is the percentile, the data is the number it actually is. So let's identify the variables in the situation. We have the kth percentile. So if I said, please find the 23rd percentile, then k equals 23. Next, the index, or I. I is going to be the answer. So if you get an index of 8, that means your answer is the 8th number in the list. If you get an index of 1, it means that it's the first number in your list, and so on. I is the answer of where the actual number is in the list. It's called an index. And n is the total number of data. So you need to know all of that info to figure out the answer to what the percentile would be. So in order, first put them all in order, then calculate this interesting looking formula. And when you do it, you're going to have two possible outcomes. Either you're going to get you're going to get a whole number, or you're going to get a number that is a decimal. So if it's a positive integer, meaning a whole number, if it's an integer, then the kth percentile is the data value in the position of the ordered data. So let's say you do that work and you get 8, then the answer is the 8th number you see. If it's 8.2 or 8 point something, then you go to the next idea. If I is not a positive integer, then round I up and round I down to the nearest integer. So if it was 8.2, you do 8 and 9. If it was 16.88, you do 16 and 17. Okay, so you would do those two numbers and then average those two values. So take the 8th number in the list and the 9th number in the list and average them, then is what you do. So that's the directive of how to find the kth percentile. Let's do an example. All right. It says listed are 29 ages for Academy Award winning best actors in order from smallest to largest. The good news is you don't have to sort them this time. They're in order. Thank you. Okay. But if they aren't, make sure you stop and sort them. Now, can you find the 70th percentile? Let's go back and look at that formula one more time. Recall that K is the actual percentile. Here will be 70. I is the index, which is going to tell you where the number is, and N is the total number of data. And the formula looks like this: I equals K times N plus 1 over 100. Let me put that in. Okay. I'm gonna have to type it just one more time. I'll put it up here. All right, so yeah, it's supposed to be plus 1. All right, whatever. It's supposed to be plus 1. Plus 1. All right. So that be the case. All right. Let's say let's find the 70th percentile. Okay. So you're trying to find the 70th percentile. Then we're going to say now K equals 70. And then we're also going to say how many do we have here? That'll be N. N equals, now there's 29. They told you that there are 29. And now you can put this all together and figure out I, the index. So it'll be I equals K, which is 70, times N plus 1, which is 29, plus 1, all over 100. Okay. So with the calculator, if I figure that out, I'm going to get 70 times 30, divide by 100, and I get 21. So that's telling you that the answer is the 21st number I see. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. The answer is 64. 64 is our answer. How would I do it for the 83rd percentile? It'll be the same thing, except right here, I put an 83. If I put an 83, then what happens there is I equals, okay, so it's 83 times 30, right? Yeah. Divide by 100. I'm getting 24.9. Okay, now 24.9 means that I have to think about, I'll put it in the blue, 24th and 25th. So I have to think about those two. So now where are they, the 24th and the 25th? Let me see. Well, we do have the 21st, 22nd, 23rd, the 24th and 25th are these two, right? So what are we supposed to do with those numbers? We're supposed to average them. What is the average of 21, of 71 and 72? The answer is going to be 71.5. So sometimes a percentile has a decimal in it that you have to put in there to show the average. Try it is a great example of trying to figure out the answers. We could do those together in class when we get together for the lab. But this is how you'd find the percentile if I gave you the actual percentile. Please find the 70th. Please find the 83rd. Now what we're going to do is we're going to talk about what it's like to go in the opposite direction, where I give you the actual data and ask you what percentile is it going to represent. Let's clear these drawings. Go to the next part. So if you're going to go to find the percentile of a value, then what you do is you order them again, put them in order from least to greatest, and then X is the number of data values counting from the bottom of the data list up to, but not including the data value you want. So when we were looking at that long list of ages, if you think about, what if I said do 38, then count all of the numbers that are lower than 38 in the list. Y is the number of data values that are equal to the data value. So that would be the actual number of 38s or whatever the number is I would call. And then N is the total number of data. I want you to notice with me right now, if you look closely right here, that in the very specific event that Y equals 0, that whole factor will just kind of disappear. And when it does happen that that factor is 0, I want you to feel not awkward about saying, okay, that 0.5 times 0 is 0, now it's gone. That happens sometimes. So remember, Y is the number of data values equal to the data value. Let's say I asked you, what is the percentile associated with 38, right? But there are no 38s in the list. Remember, that's okay, because to find X, you have to count how many numbers are less than 38 in the list. You don't even care if 38 is in the list. You just need to find out how many numbers are less than 38 in the list. So if there are no 38s in the list, then Y equals 0, and that becomes 0. And that's okay when you're doing percentiles. So just remember that there's every so often you'll come into a situation where the number you're asked about is not in the data. And when that happens, the consequence is the Y is 0 and the 0.5 disappears in the formula. All right, so keep that in mind. Let's do an example of it. And that formula is X plus 0.5 Y slash N. I'm going to put it right here. right now. Again, here's the same data, 29 actors, okay? And we're going to talk about 29 actors that won Best Academy Awards, right? Best Actor. Find the percentile for the number 58. Find the number for the percentile 25. Now notice in both of these cases, I just want to point out, and this is kind of important, in both of these cases, we do have the figure, actually there's a 58. And we also have 25, there's 25 right there, see that? So in both of these situations, A and B, you're not going to have a situation where Y is 0. In fact, in both of them, if you look, Y does equal 1. So just be ready for that if that happens. Okay, let's do part A. A is going to say, find the percentile for 58. I have to count how many are behind 58. So I'm going to use the check mark and just kind of count them. Here's 58, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, I found that there were 18 of them. So that means that in this case, X equals 15, Y equals 1, and also N equals 29. So we could do the math now. Modeling that equation up there, I have 15 plus 0.5 times 1 over 29 times 100. All right, so with the calculator, let's see if we can figure that out. What would that be? 15.5 divided by 29 times 100. I'm getting 53.44. Okay. So now, the answer is 53.4. Now let's take a look at what it says about rounding with this. Let's just take a look here. We'll go back for a minute. Round to the nearest integer. So what happens when you round 53.4 to the nearest integer? You get 53. So what is the percentile for 58? It's the 53rd percentile. And that does kind of make sense a little bit, because if it's the 15th figure and there are 29 figures, it's about halfway through, and 53 is almost 50%. You could do that also now with 25, using X equals 25, Y equals 1, and N equals 29. All right. Okay, so that's everything you need to know about percentiles, friends. I hope that that helps. Also, there's a try it there. I strongly recommend that you try that. There's one more thing we have to do, and that's talk about how to do box plots. But I would like to give you guys a little bit of a break. So let's take a little bit of a break. I'll leave this all here so that you can continue to look at this. When we come back, we'll only need about 10 more minutes of instruction, and then we'll be done with box plots, and then we can break away and work on practice if we want, or do other things. Right now, we're going to take a little break. It is 6:05. I'll ask that you return at 6:15. Welcome back. We're about to talk about how to do a box plot now. And the box plot is also called a box and whiskers plot or a box whisker plot. And basically, they follow the concept of quartiles. So box plots give a good graphical image of the concentration of data. They also show how far from the extreme values are the most of the data. A box plot is constructed from 5 values: the minimum value, the first quartile, the median, the third quartile, and the maximum value. Here's an example. Construct a box plot for the following data representing the heights of 40 students in a statistics class. So here we have them in a nice perfect order. If we took those numbers and tried to figure out what the quartiles would be, it would look kind of like this. First, I'd have to examine the median or quartile 2 using this number and this number. And they are the same number, but the average of those numbers is going to be, of course, 66. All right. Now, since we have 66 to cut our data into 2 equal parts, the first of the 2 equal parts is the first 20 numbers, and then the second of the 2 equal parts is the last 20 numbers. So first, let's think about the first set of 20 numbers. I'll use blue to show this, and we're going to think about this number and this number, and that's why we're going to say that Q1 is the average of those 2 numbers, which is 64.5. Next, I'll use purple to try to illustrate the third quartile or upper quartile using these numbers, 70 and 70, and they are the same, and the average of the 2 being obviously 70. So now we could say Q3 equals 70. All right. So now I have the 3 quartiles. Great. If I want, I could go a step further and go find out if there are any outliers. Looking at this set, though, I can kind of tell the data are pretty kind of packed together, and I don't see any weird numbers. Most of the numbers are kind of just in line with kind of how they should be. Seems like a pretty consistent spread. So I wouldn't think there might be outliers here. It's a little bit of a waste to test it out. So let's take these 3 figures and let's try to create a box and whisker plot. The way that you should do that is try to come up with a number line that encompasses all the data. Starting with how the lowest number is 59 and the highest number is 77. You might want to elect to choose numbers that are going from 50 to 80 in 5s, because then you'll cover everything. So let's see if we could do something like that with text first. So I have 50, 55, 60, 65, 70, 75, 80. Right? Let me spread them out a little bit. Spread them out a little bit. Great. Okay, so you have a nice little number line there to represent all of the numbers, and if you wanted to, you could plot them all on there because you've covered the distance from the lowest number 59 all the way up to the highest number 77. You have that all there. Now what you want to do is you want to take these quartiles that you see here, okay? And for each of those 3 quartiles, you're going to take a vertical line slightly above the number line here. Kind of like this. For 64.5, that ought to be kind of like right about here. For 66, that ought to be kind of like about right here. Maybe not. Maybe more like this, right? Then for 70, of course, it is specifically right there. Okay. Then the last thing you want to do is you want to consider the very first number in the set 59 and the very last number in the set 77. So let's represent 59 with a vertical line. Good. And let's represent 77 with a vertical line. Okay, let's stop here for a minute. So we're constructing a box and whiskers plot. Note, what I did was first I drew a number line and I deliberately chose numbers in a decent counting range that encompassed all the data from beneath the lowest to beyond the greatest, going from 50 to 80. Then I took vertical lines of each of the 3 quartiles and the lowest number and the highest number and put them above. Now I have to connect them and make a box and whiskers plot. It looks like this. Okay, I'm trying here. Help me. It requires a steady hand. Hold on, hold on. Here you go. That's what it looks like. Yay, geometry. Okay, so that's what it would look like. The box, of course, is in the middle. It represents the three quartiles. The whiskers represent the spread outside of the quartiles. And now you have a beautiful box and whiskers plot. When you use Excel to make a box and whiskers plot, it gives them to you vertically. So it's just what you're looking at, but imagine if it looked like this. It's funny how the boxes are in the middle and the whiskers are like this. They look a little bit like Christmas ornaments, kind of, because of that. But the original way that we're supposed to learn about box plots is what you're looking at here, and this is what they expect when you do a box plot, okay? Or a stem and box and whiskers plot, however you want to call it. Okay, like I said, I didn't have that much more to talk to you about, but that is everything that we need to know about chapter 2. And now what I'd like to do is talk to you briefly about what you can expect in the future. Let's take a quick look right here at our e-learning Blackboard shell. You'll see in here that right now we're on Monday, where we were supposed to study chapters 2.1 through 2.4, which is just what we did. We had a great conversation about all that material. The next thing we're going to do will be right here. So when we get together on Wednesday, which will be in person, down in Cape May County on the campus. When we get together there, we'll do chapters 2.5, 2.6, and 2.7. And then next week on Monday, when we get together, we're going to do all the labs and all of the homework assignments associated with it in class. And if everybody comes and participates and pays close attention and works with the group, everyone will get full credit for that. And we do require that you come to all these classes, of course. And then last but not least, we're going to have our review next Wednesday. And then Monday, the 14th, will be the day of your exam. So we're right on schedule where we expect it to be. Today, we conquered chapters 2.1 through 2.4. And now, if you go to right here, let me get rid of that now. If you go here to where, let me give you student view. Hold on a minute. You're looking at the teacher's view. In student view, if you go here to unit 1 and go to chapter 2, probably in somewhere around 2 or 3 hours, right here in this area, you'll see a link to this video that you're watching. So you could go back and watch it again, and you could pause it, and you could look at what was written and all of that. And if it helps you, you could think of questions and ask them on Wednesday when we get together, okay? So that's all I have for you, my friends. I'm going to stop the share here. I'm going to stop our recording. And then after I stop our recording, we'll open the floor to questions, and then we're dismissed. Once again, thank you so much for your close attention to my lesson.